Okay, welcome to Udemy Chemistry class, and this is a tutorial on CH111 or inorganic chemistry, and this is prepared by Dr. Mara Emmanuel. Here, I am the instructor. I am going to present whatever is prepared for the students here. Now, within this course in organic chemistry, we aim to introduce the foundational concepts basically of inorganic chemistry, focusing on topics that will be essential for teaching high school students. Emphasis will be placed on periodic table, atomic structure, chemical bonding, acids, bases, salts, and coordination chemistry. Atomic structure is a foundational topic in organic chemistry. So understanding how atoms were discovered, their internal structure, and how electrons are arranged around the nucleus is essential for explaining chemical bonding, periodicity, and the reactivity of elements. So, learning this course, by the end of this lesson, students should be able to describe the historical development leading to the discovery of the atom, identify and explain the properties of subatomic particles, protons, neutrons, and electrons. And also, the student should define atomic numbers, mass numbers, and isotopes, and apply this concept to simple problems. Know also to write the electronic configuration of elements, relate them to the periodic trends. So, in organic chemistry, to begin with this chapter in lecture 1, the discovery of the atom. Early ideas about matter. The early ideas about matter. We have a Greek scientist, ancient Greek philosopher, Democritus, with this time 400 BC, proposed that matter is made up of tiny indivisible particles called the atoms. This idea was philosophical and lacked experimental evidence. We know atoms are very, very tiny indivisible particles. That means they cannot be divided into further. Okay, he proposed this. And he gave the name those atoms to be atomos. The idea of Democritus was very philosophical, and the challenge of this idea is that it lacked experiment. Come to Dalton atomic theory. This provided the first scientific atomic theory. So why do we call this is the first scientific theory? Because the ideas of the Dalton was very scientific. That matter is made up of 10 indivisible particles, again, but called atoms. All atoms of given element are identical in mass. Consider this idea that Dalton proposed. All elements are identical in mass, something which proved wrong by the recent science that not all atoms in the periodic table have identical mass. Atoms combine in simple whole numbers ratios to form compounds. Again, Dalton proposed that atoms can combine in simple whole number ratios to form compounds. Again, this idea was recently proved wrong because not only atoms can combine in simple ratio, but also can combine in larger ratio to produce large compounds. The chemical reactions involve rearrangement of atoms, not their creation or destruction. Also, Dalton proposed that the chemical reactions involve rearrangement of atoms, only that, but not creation or destruction. This is contrary to the recent experiments, which also proved wrong that not only rearrangement occurs in atoms, also creation and destruction is possible. And this is where chemistry is coming. That chemistry, they study composition and decomposition of matter. So we create and we destruct. So the idea proposed by Dalton was very scientific to find the pre-foundation of knowledge. That's why recent researches and research experiments proved it wrong. Now, limitation. Dalton did not know about subatomic particles or isotopes. This was the limitation that Dalton atomic theory is coming with. So, a recently development of atomic models is coming to create a gap and correct those theories proposed by Democritus and Dalton. Before 20th century, the atom was considered the smallest indivisible unit of matter based on Democritus and Dalton's ideas. Three groundbreaking experiments between 1897 and 1913 completely reshaped this view in the following. Consider J.J. Thomson, 1897, the discovery of the electron. Here, the electron was discovered. The experiment was performed as follows. A sealed glass tube with most air removed, containing two metal electrodes. Okay? Two metal electrodes. That means he created a tube, right? He created a tube. And he created a tube. Within this tube, he designed these two metal electrodes. That means from the concept of electrochemistry, we know electrodes. That means we have positive electrode, and the negative electrode, right? Positive electrode and the negative electrode, right? With this, when a high voltage is applied, when a high voltage was applied to this system of the electrodes, a glowing ray was produced, traveled from the cathode negative. That ray traveled from the cathode negative to the anode negative. So suppose the cathode negative is here and the anode positive is here. And these rays, due to construction, were traveling from the cathode to the anode. With this continuation, what was the observation? The rays traveled in straight line. First of all, these rays traveled in straight line. That means from this region to this region. They could be deflected by electric and magnetic fields. Okay? These rays could be deflected by electric and magnetic fields. Now, the deflection direction showed the rays were made of negatively charged particles. These rays, which were moving from this electrode, negative electrode, to the positive electrode, carried the charge, carried the negative charge, carried the negative charge. So, the moving ray from cathode to anode contained the negative charge. What was the conclusion? Thomson had discovered a fundamental subatomic particles, the electron. Its mass was much smaller than the lightest atom, which is hydrogen, providing atoms were not indivisible. C. Why atoms are not indivisible? Because here its mass was much smaller than the lightest atom, taking hydrogen, providing atoms were not indivisible. Okay, right. Now, the Plum budding model developed in 1904. Analogy. Think of the positively charged padding, the atom as a wall. Okay? Think of the positively charged padding, the atom as a wall with negative charged plums, which are electrons, embedded throughout it. So the Plum budding model described that. Think of a positively charged padding, P, the atom of the wall, the positive charged like this, the positive charged. We might take a positive charged padding. This might be taking an example, and with negative charged plums, that in this, predicting the shape of the atom, it was previously set like this. That atom exists in this way. It has plenty of electrons, which are particles, and protons inside. Okay? The model. The atom was a uniform, positively charged sphere with negative charged electrons scattered inside it. So it's a sphere. It was proposed as a sphere with the positive and negative charged protons and electrons. The significance of this was the first model to propose an internal structure of the atom and introduced the concept of subatomic particles. So here we find that with this model, we got subatomic particles, which are electrons, protons, inside the sphere of the atom. Now come to Ernest Rutherford, 1911, the discovery of the nucleus. Now again, the nucleus is discovered. The experiment, Godfoil scattering. The experiment Godfoil scattering was set like this. Rutherford and his students, Kagan, Madsen, fired a beam of positively charged alpha particles at an incredibly thin sheet of gold foil. A fluorescent screen surrounded the foil to detect where the particles went. Right. The expectation, based on Plum padding, that the alpha particles should pass straight through or be deflected very slightly by the diffuse positive padding. And the shocking observation was that most alpha particles passed straight through. The atom is mostly empty space. The most alpha particles passed through. Because remember previous we said, according to the Plum padding model, the atom exists as a sphere, and it's like positive and negative charged particles are suspended within it. Now this experiment with Rutherford fired a beam of positively charged alpha, a beam. That means when you fire a beam of positive charged alpha, come like this. When you fire like this. That means you allow a beam of positive charged alpha from this side to go inside the sphere of the atom. Okay? If that was set by Rutherford. Okay. Now, The most interesting thing here in Ernest Rutherford, it was almost as incredible as if we fired a 15-inch shell at a piece of tissue paper and it came back and hit you. See? That means to interpret this, the only way to explain the backward bounce was if all the positive charge and almost all of the atoms' mass were concentrated in an incredibly tiny, dense center, must be the nucleus. You see? To clarify this concept, I can take some time, I can take here that suppose this was to be taken as an atom. Remember, we said it was according to this model, the Plum budding model proposed that atoms have positive and electron have positive charged and negative charged particles in the sphere, right? So, if they fired a beam of positively charged alpha particles, that means if you fire here a beam of positively charged particles, what do you expect? The observation is shocking because we are not expected. If Plum padding model proposed that the sphere is suspended with positive and negative charges, now we expect that when we fire the beam of positive charged alpha particles will either pass through the sphere, that means the atom space is empty, is nothing inside. And what was the observation? Okay, the observation was that most alpha particles passed straight through. That means the atom is almost empty. The atom is almost empty. Why? Because this is positive. The coming beam of positive charge is positive in charge. It's suppose it lights here. It bombards these atoms, of which we have proposed that they contain plus, minus, or positive and negative charged particles. Remember, unlike charges attract and like charges repel. That means we expected that if all the sphere, the entire sphere contains the plus minus charged particles, either this will deflect at any point. But the observation was shocking. Most alpha particles passed through. That means the large number, 90% of the fraction of the beam of positive charged particles passed through the atoms. That means everything in the beam was allowed to pass. Most of it was allowed to pass. Only small fraction were deflected at large angle. Only small fraction was deflected. And that small fraction was concentrated at the center of the atom. And that is where the nucleus was discovered. See? This diffraction was at large angle. You see? That means we are expecting this A, the coming beam, to penetrate these atoms and to come to side B. You see? We are expecting that this beam of positive charged alpha is lighted to the atoms. We expect that it will pass through because the entire sphere is nothing. Okay? That means it is an empty space. Now, what was the observation? Observation shows the entire beam of positive charged alpha were passing through this space in the atoms. But at the center, the small fraction were deflected. This marked the discovery of nucleus. That means within an atom, there is a concentration of positive charged particles, of which the coming beam was positive, and the positive charged neutron nucleus here. That means it is concentrated with the positive charged ions. That is why diffraction occurred. Right. This was Ernest Rutherford experiment, and their assumptions and their conclusion led to the discovery of nucleus. Now, the nuclear model, the atom consists of thin, dense, positively charged nucleus at its center. Okay. Now, we discover the position of the nucleus is that it is at the center by using Rutherford experiments. And within the nucleus is where positive charged particles are concentrated. Because the passed beam positive charged to the atoms where almost the entire beam particles passed through the nucleus. They passed through the sphere. And a small portion of it deflected at the center of the atom. That means it contains nucleus and also it contains positive because like charge repel. The negative charged electrons orbit this nucleus at a relatively large distance. So that means together with the discovery of the nucleus, outside the nucleus, there is electrons that is surrounds this nucleus. The atom is mostly empty space. Those are the nuclear model assumptions. The problem with Rutherford model, according to classical physics, an orbiting electron, a charged particle, should continuously lose energy as radiation and spiral into the nucleus within a fraction of a second. See that the problem with a position of electron in a sphere of the atom is coming. The challenging position or determining the position of the charged electron particles in the sphere of the atom is very, very challenging. So the Rutherford model was not completely describing the position of electron in the sphere. This meant atoms and therefore all matter should be unstable. They aren't. A new model was needed. See, we required the new model to determine the position of electron in the sphere or in the entire sphere of the atom. Now, see, this scientist Neil Bohr principally quantized the orbits. He quantized the orbits in order to study the exact position of electrons in the entire sphere of the atom. So, this is a bridging gap. Bohr, a student of Rutherford, applied the new idea of quantum theory from Max Planck and Albert Einstein. So, to solve this stability problem, we required another model which basically performed to quantize orbits in order to study the properties of electrons. The Bohr model of the hydrogen atom suppose Bohr proposed these voluntary postulates that electrons can only exist in specific stable orbits, which we call shells, around the nucleus. So atoms in the nucleus have specific paths, which are called stable orbits or shells, around with the nucleus. These are stationary states. Why do we call stationary states? Because the position of the electron in the orbits, the orbits are not moving. These orbits are not moving. Only electrons are circulating around these orbits. So we call them the stationary states of atoms. The stationary states of electrons in the sphere of atom. Electrons do not radiate energy. Electrons do not radiate energy while in these stable states. We call them they are stable because they are not moving in when the electron jumps from a stationary phase, from the stationary state to another stationary state. That means it will radiate energy. But with a stable electron in its position at a stationary phase, which are shells, that means the electron, the atom, will be stable. An atom is only stable when its electrons are in these allowed orbits. Now, energy is absorbed or emitted only when an electron jumps between these fixed orbits. The energy change is a discrete or packet or quantum of energy equal to the difference between the two energy levels. So suppose this is the graph, okay, showing energy level difference, okay, that this is energy level 1, this is energy level 1, and this is energy level 2, okay, and now this is energy level 3. These lines, red lines, represents stationary states of atoms, the stationary state of atoms. And in these atoms, in these stationary states of atoms or orbits is where we find electrons. So if this is n is equal to 0, right? Energy level 1, that means orbit 1, where there's maximum possibility of finding electron. This electron here in this orbit is stable because the electron is existing in its stationary state. If it comes, this electron jumps from the stationary state to either Ne2, that means to the second stationary state, or the same electron jump to Ne3, the second stationary state. Now this entire atom is unstable because electron jumps from the stationary state to the next stationary state. And the energy associated with the absorbed or emitted radiation is directly proportional or is equal to the difference between the energy levels or the shells or the stationary states where the original atoms exist. So this is the energy, okay? Right. Now, the key features and success. Quantization. Energy levels are like steps on a ladder. An electron cannot exist between steps. C. Explained atomic spectrum. The model perfectly predicted the discrete line spectrum of hydrogen. Each spectral line corresponds to an electron jumping from a higher to a lower energy level, releasing specific amount of energy as light. Now, introduce the principal quantum number, labeled the energy levels n equals to 1, 2, and 3, with n is equal to 1 being the ground state, which is the lowest energy. So with that means if we consider this, introduce the principal quantum number, this number n is nothing but represents the energy levels. Okay? Limitation of Bohr's model. It worked beautifully for hydrogen. That the study of one electron in hydrogen was very easy. So, but failed to accurately predict the spectra for atoms with more than one electron. Now, the complication comes. If you want to study more than one atoms, how does this occur? In summary, scientists with experimentation, what did they discover? Okay, their model and their major contribution. Okay, now J.J. Thomson, his experiment was cathode ray tube, and what was discovered? Electron, negative charge, very small mass. Okay, the Plum body is another atomic model is coming. Okay, and helped to predict the structure of the atom. Now, the major contribution and limitation of this is that atoms have internal structure, not indivisible. Model was incorrect. This is the limitation. Ernest Rutherford performed the experiment called gold-fold scattering, and the discovery was dense positive nucleus. Atom is most empty space. Okay, the idea that the atom is mostly an empty space, and at the center we find the nucleus. This was very, very basic foundation for studying atoms. And the atomic model is a nuclear model, and the major contribution, discovery of the nucleus, but its limitation is that could not explain atomic stability. For the Bohr, who is a student of Rutherford, now analysis of hydrogen spectrum, this was a setup experiment. The key discovered electrons in fixed energy levels, quantized jumps. Okay, electrons in fixed energy levels, that means stationary states, and they can be quantized. And the atomic model in Bohr is that planetary Bohr model. His major contribution explained atomic stability. Okay, that if electrons are in the ground state or in stationary states, that means it is stable, unless it is quantized, and that is where instability of the atom is coming by studying the hydrogen spectrum. But another limitation for this is that the study was basically for one electron in hydrogen spectrum, and now it was more complicated to study the multi-electron atoms. Now, with this, a prompt question is coming. Early scientists knew atoms emitted light when heated, but Rutherford's model predicted atoms should collapse instantly. Bohr proposed a solution. Electrons exist only in specific energy levels. Now, predict what happens when an electron gains energy. What happens when it loses energy? Draw a diagram showing your prediction. At this is a part 1 for lecture 1, and please work on this prompt question and submit in a next lecture. Thank you.